I'm going to go through this example problem where we use vapor-liquid equilibrium data to estimate the two-suffix Margules parameter A. In this problem, we're given experimental data of a binary system of benzene and cyclohexane at 60 degrees Celsius, where we're given the pressure at different liquid and vapor mole fractions of benzene. The first step in any vapor-liquid equilibrium problem is to write the master vapor-liquid equilibrium equation and to simplify the terms of the equation as much as we possibly can. From the experimental data given, we can see that the pressure of the system is going to be around 0.5 bar for all compositions, and this is low enough to safely assume that the vapor behaves ideally. And since the vapor behaves ideally, that means that we can neglect this vapor fugacity coefficient term and assume that it will reduce to 1. The next term in the equation to try and simplify will be the fugacity of pure species I in the liquid phase. The exponential term in the liquid fugacity equation, the Poynting correction, is negligible for system pressures of less than 100 bar, so this term is going to be negligible for this problem. Now we need to calculate the saturation pressures of both species in order to determine if the fugacity coefficient in the liquid fugacity term is going to be negligible. Using the data for Antoine's equation in the back of the book, we can calculate the saturation pressures of benzene and cyclohexane at 60 degrees Celsius, and you'll get the following answers. Since the saturation pressures are so low, this confirms that we can neglect the fugacity coefficient at saturation. Applying the simplifications that we made, this is our now reduced vapor-liquid equilibrium equation. We can now rearrange this to solve for the activity coefficients of species 1 and 2. Now that we know how to calculate the activity coefficients of both species, we can calculate the excess Gibbs energy of the mixture using the equation for the excess Gibbs energy of a binary mixture. In addition to this expression for the excess Gibbs energy that we have in terms of the mole fractions and the activity coefficients, we also have another expression for the excess Gibbs energy that's in terms of the liquid mole fractions and the two-suffix Margules parameter A. This equation can now be rearranged to solve for A. So since we're given multiple data points from the problem statement, the procedure that we're going to take is we're going to use the equilibrium data to calculate the activity coefficients of each species at each data point, then using these calculated activity coefficients to calculate the excess Gibbs energy. From there, we're going to plug in the excess Gibbs energy that we solved into the equation to solve for A, and we're going to basically calculate a value of A for each data point, and we're going to average the A's calculated for the effective two-suffix Margules parameter. The quickest way to do this would be through Excel, so I'm now going to import the equilibrium data that we're given into a spreadsheet and go through the calculations to find our final answer for A. Starting with the raw data that they gave us in the problem statement, x2 is going to be equal to 1 minus x1 because it's in a binary mixture. y2 is equal to 1 minus y1. The activity coefficient of species 1 is going to be equal to y1 times the total pressure of the system divided by x1 times the saturation pressure, which the saturation pressure for species 1 was 52,187 pascals. Calculating gamma 2 is going to be the same equation, just using everything for species 2. To calculate the excess Gibbs energy, we're going to use R times T times x1 times the natural log of gamma 1 plus x2 times the natural log of gamma 2. Now calculate the product of x1 and x2 at each data point. A is equal to the excess Gibbs energy divided by x1 times x2. Now to get our effective value of A, we're going to calculate the average of all of the A's calculated at each data point. And this is our final answer for A. From this model, using the experimental data, we're able to estimate that the two-suffix Margules parameter A is approximately 1,140 joules per mole. I hope you learned something from this video and that it helped you understand how to solve the problem. If you liked this video, give it a thumbs up and subscribe for more content in Chem E 211 at Purdue University.